topic of tolerances in engineering is closely related to the topic of limits in calculus. We're going to do a couple of applications about tolerances and tie it into the definition of a limit. In this example, we're designing playground equipment, and we're going to build a large plastic cylinder. The height is 1.5 times the diameter of the cylinder, and the volume needs to be 8 cubic meters. Now, the volume of a cylinder is a circle with some height, so the volume will be area of the circle base times the height. And for this particular cylinder, the height is 1.5 times the diameter. We will be interested in the diameter because for a solid object, it's much easier to measure it than to necessarily try to pin down the radius. You can get the diameter and divide by 2 if you really wanted the radius. So we're going to rewrite pi r squared as pi times diameter divided by 2 squared, and then we're going to multiply by the height, which is 3/2 or 1.5 times the diameter. If you clean that up, notice the 2 in the denominator of d over 2 squared will become a 4, and 4 times 2, because there's another 2 in the diameter of the 3/2, will give us a denominator of 8. And so the formula cleans up as 3 times pi over 8 times d cubed. So we want to find the exact diameter to make this plastic cylinder of 8 cubic meters. So we're going to set our volume formula in the previous slide to 8, and we're going to solve for d. So multiply both sides by the 8 that's in the denominator, and you get 64 on the left-hand side. Then divide by 3 times pi, and that will give you 64 over 3 pi equals d cubed. Therefore, the cube root of 64 over 3 pi will equal d. Is this an irrational or a rational value? It's irrational. The cube root of 64 is 4, and that is a rational number, but in the denominator we have the cube root of 3 times pi, which is irrational. So the overall value is irrational. That means that it is not possible for us to create this exact diameter in the real world. Instead, we would have to just get as close as we wanted to. So suppose we were interested in getting as close as the 10,000th place. So rounding that value to the 10,000th place, it's approximately 1.8937 meter diameter. Now, anytime you're trying to cut something or create something that's an irrational value, you have to settle on some tolerance. So in this case, suppose our volume could be off by 1/2 of a cubic meter. We're going to find the upper and lower bound of the diameter to keep the volume within our tolerance of 0.5 cubic meters of our 8 cubic meters. So if the volume could be off by 1/2 cubic meter, that means that it could be as low as 7.5 or as high as 8.5. Setting both of those values equal to our volume formula and solving, 7.5 times 8 is 60, divide by 3 pi, and then take the cube root to get d. The lower bound is the cube root of 60 divided by 3 pi, or approximately 1.8534 meters. The upper bound will be 8.5 times 8, or 68, divided by 3 pi, and then to get d, take the cube root, and the upper bound of the diameter is approximately 1.9323 meters. If we were going to state just one tolerance that could be used for the upper or lower bound, we would actually want to use the upper bound for the diameter and its difference between that and our ideal diameter of the cube root of 64 divided by 3 pi. The function is a cubed function, and so cube functions get steeper as your input gets higher. So the upper bound is going to be closer to our ideal than the lower bound. The difference between the upper bound and the ideal is approximately 0.0386 meters. So we can be off by, almost 4/100ths of a meter or 4 centimeters in terms of the diameter. If we relate this problem to tolerances and the definition of a limit, the limit is the 8 cubic meters that we're trying to reach as the exact volume. The input that would be needed to get that exact volume is our A. So when we say the limit as x goes to A, the A in this case would be the cube root of 64 over 3 pi. We wouldn't really be able to cut that exact diameter, and so it could be off by delta, or 0.0368, and keeping our diameter within 0.0368 of our ideal diameter, then the volume would be off by no more than 0.5 cubic meters. So epsilon is 0.5 cubic meters. Epsilon is the tolerance around the output, and delta is the tolerance around the input. Looking at another example about tolerances, this time about finances, we have $8,000 to invest and we want it to grow to $16,000 in 10 years. We want to make certain that the amount grows with no chance that it will decrease in value. So we will invest in a CD that pays interest monthly. Find the rate of interest for the CD to meet our goal of $16,000 in 10 years. The compound interest formula is given below, assuming we begin with a principal of $8,000 and we earn monthly interest, hence we'll divide our interest rate by 12, and the exponent will be the number of times a year you're granted interest times how many years, so 12 times 10. To find the exact rate needed for our $8,000 to grow to $16,000 in 10 years, set the compound interest formula equal to 16,000. Then we'll divide both sides by the 8,000. That isolates the power of 120. To undo the power of 120, we need the reciprocal power, so we'll raise both sides to 1 over 120th power. That gives us 2 to the 1 over 120 power. And on the right-hand side, we now have 1 plus r divided by 12. Subtract 1, and then multiply by the denominator of 12, and we have solved for r. Is this an irrational or a rational value? It is irrational. So the best that we can do is round it to some decimal. We're not going to be able to hit that exact rate, but rounded to the 10,000ths place, the number is 0.0695, or in terms of an interest rate as a percent, it is 6.95%. Finding an interest rate of 6.95% for a CD is a bit unrealistic in this day and age, so we may need to figure in a little bit of wiggle room. Now, if we made more than $16,000, it wouldn't matter, so we're more concerned about the lower bound. Hence, let's only worry about finding a lower bound for the rate. So $1,000 off of $16,000 would be $15,000. Let's suppose we make that as the low end of our goal. So set the compound interest formula equal to 15,000, then divide by 8,000. Notice the thousands cancel out. Undoing the power of 120 again, you use the reciprocal power. Then subtract 1 and multiply by 12 to isolate the r. Once again, that's an irrational number. It's approximately equal to 0.0630. So we could lower the interest rate a little bit, but we may want to actually start looking into other investments besides CDs. So the tolerance for our output of $16,000 was $1,000. The tolerance for the interest rate turned out to be 0.65%, or 0.0065. That's the difference between the ideal interest rate that would give us $16,000 exactly and the interest rate that would give us our lower bound of $15,000. If you relate this to the idea of taking a limit, in this case, we would actually be taking a limit from the left-hand side because we're only interested in the lower bound. Our limit is the 16,000 we're hoping to earn. Our A, or our ideal input, is exactly 12 times the quantity 2 raised to the 1 over 120 power minus 1. Again, that's an irrational number that is not technically approachable. It was approximately equal to 0.0695. The epsilon is how much our output can be off, and it was $1,000. And that gave us a tolerance around the interest rate of 0.0065. Let us talk through an epsilon delta proof of the limit as x goes to 7 of the polynomial 4x squared minus 3x plus 5 equaling 180. What we're trying to do is we're trying to prove that no matter how close to 180 we make the shown lower and upper bounds. Notice there are 3 horizontal lines drawn in the graph. The middle one is at exactly 180, and then there's an upper bound and a lower bound drawn. So our proof is going to show that no matter how close together those 3 horizontal lines are, we'll always be able to find some interval around 7 such that all of the x's that fall in that interval around 7 guarantee us function values that fall within the upper and lower bound around 180. Reminding about our definitions of epsilon and delta, we can restate what we just stated in the previous slide, that we're trying to show that no matter how small of a tolerance around f of x equals 180, and we're calling that tolerance epsilon, we can find a tolerance around x equals 7, and we'll call that tolerance delta, so that all values within delta of 7 compute f of x values within epsilon of 180. Notice we've labeled on the graph now what is epsilon and what is delta. They're the distances from the ideal in the y direction and in the x direction. Remember, absolute value means distance. So for example, the absolute value of 5 means the distance of 5 from 0. So when we write the absolute value of f of x minus 180, we mean the distance between f of x and 180. So that distance in this case will be for the absolute value of 4x squared minus 3x plus 5, because that's our function, minus 180. If you clean that up, you get the absolute value of 4x squared minus 3x minus 175. You can factor that polynomial as 4x plus 25 times x minus 7, and the absolute value of a product is the same as the product of the absolute value of the factors. So I can break that up as the product of those two factors in absolute value. So we have the absolute value of 4x plus 25, and we just got done saying that absolute value really means distance. So the absolute value of x minus 7 means the distance between x and 7. So the absolute value of f of x minus 180 is equivalent to this factor 4x plus 25 times the distance between x and 7. So we just showed that the distance between f of x and 180 is equivalent to the factor absolute value of 4x plus 25 times delta. Since x is close to 7, then 4x plus 25 is not going to be just anything, it will be close to 53. Where we're getting that is that x is close to 7. So 4 times x is close to 28, and then you add 25, you get 53. Then also consider that dividing by a larger number creates a smaller quotient. So let's choose a number slightly larger than 53 to replace the 4x plus 25. Then as we take the limit as x goes to 7, the distance between f of x and 180 is going to be less than some value slightly larger than 53 times our delta. Since we want the distance between f of x and 180 to be less than epsilon, And considering that we just showed that the distance between f of x and 180 will be less than some number slightly larger than 53 times delta, choose delta to be epsilon divided by 53.5. Again, the 53.5 is just a number that is slightly larger than 53. Then the distance between the function and 180 is equivalent to those two factors. The absolute value of x minus 7 is delta, and we know that 4x plus 25 should be less than 53.5, because as you get very close to 7, the value of 4x plus 25 is going to be very close to 53. So at some point it passes up 50, or it becomes lower than 53.5. Since we're choosing delta to be epsilon divided by 53.5, then if you look at how the 53.5s divide out, we just proved that the distance between f of x and 180 will be less than our epsilon if we let the tolerance in the x direction be epsilon divided by 53.5. So for example, let's suppose we wanted to be within 0.02 of 180. Then pick delta to be 0.02 divided by 53.5, and that is approximately 0.000374. So then choose a value of x that falls in that interval. For example, 7.00003 is within 0.000374 of 7. If I plug 7.0003 in for x, I get 180.0159, and that is closer to 180 than 0.02. So that's just an example that using delta to be epsilon divided by 53.5 is going to guarantee that our y values are within 0.02, if that was our epsilon, of 180. A main purpose of this epsilon delta topic is to get calculus students used to the flow of a theoretical proof, just to get you exposed to theoretical proof, so those of you moving on to higher level math start to become used to doing proofs. Also, there's some common notation. Epsilon you should associate as a tolerance around your output, and delta as a tolerance around your input. And I hope by now you also realize that the true use of absolute value is to represent distance.